it's clear from my side. Please tell me about yours. I hope it is clear. Please tell me about audio and video, everyone. Okay, so in today's session, we will discuss about long transmission line. Okay, this topic is understanding of long transmission line. So we have to understand some important concept of long transmission line. Okay, so that we will cover in today's session. Okay, guys. So let's start this session, and let's first cover the introduction part. This is my introduction. My name is Asu Jangda, and I teach almost every subject in electrical engineering. You can start your preparation with me. We are going to start one series for GATE 2024, and you know that in 2002, 8 and 16 ISC Bangalore conducted the GATE exam. So we are trying to cover those years of previous year questions. Okay, so this will be starting from 23rd of August. So you can start with us, and you can join this series. This will be on YouTube. It will be free of cost. You can give the scholarship test, guys, if you are financially not that much strong, and if you want to join BYJU'S exam prep, then you can give the scholarship test and get the scholarship up to 90%. And this scholarship test will be on 20th of August from 9 AM to 9 PM you can give. And you have to register for it. For registration, you can go to the link. Link is given in the description. Okay, and from there you can register yourself. There is free workshop on 20th of August, and this workshop will be all about all about data science and artificial intelligence for GATE 2024, because this topic is included now. So you can get the information about this this course, and this workshop will be taken by Rakesh Talleja sir. So you can join this workshop. It's free of cost, and it will be at 12 PM on 20th August. Okay, so guys, let's start today's session. So in today's session, I told you that we are going to discuss about long transmission line. So let's take the long transmission line first. Okay, because the analysis of long transmission line is different from short transmission line and medium transmission line. Okay, that's why long transmission line is a bit different. Why it is different in long transmission line? It's for electrical engineering students. So I'm taking 50 hertz supply, and I'm taking long transmission line. Long transmission line. Now tell me, guys, at 50 hertz, when you say that the line is long transmission, obviously according to the length, if length of the line is greater than 250 kilometer, it's just approximate idea. Okay, if length of the line is greater than 250 kilometer, then we call long transmission line. Now to analyze the long transmission line, the first thing is you cannot lump the long transmission. Lumping model is not allowed here. Okay, what do you mean by lumping model? If you look at the short transmission line or medium transmission line, in short and medium transmission line, you have drawn the circuit of long, you have lumped the short transmission line like this. Okay, this is my short transmission line. Short transmission line. So you have represented this series impedance. This is the sending end voltage, this is the receiving end voltage, sending end current and receiving end current. So you have shown the short transmission line like this. Similarly, you have medium transmission line. In medium transmission line, we have used the nominal model, nominal pi model and nominal t model to represent. Again, it's a lumping of the transmission line. Whatever the transmission line is, I mean, it should be greater than 100 kilometer, less than 250 kilometer. So that transmission line can be lumped like this. Okay, this is my series impedance, and these are the admittance Y by 2 and Y by 2. This is sending end, this is receiving end, this is sending end current, this is receiving end current. Okay, you can make one more model. Okay, you can make T model of nominal T model for medium transmission line. So this is the line admittance, this is Z by 2 and Z by 2. Okay, so we have calculated, we have lumped the entire line. This is called lumping. It means the entire line can be represented in a small diagram. Okay, but in long transmission line, you can't do that. In long transmission line, if the line length is very large, if you have long transmission, let me show it. This is a single phase long transmission line. So in case of long transmission line, let's say this is the sending end, this is the sending end, and this is the receiving end. Now the problem is the length is very large. Because of that you cannot lump it. You cannot make the diagram like this. You cannot show it in a single resistance, inductance, capacitance. You can't do that. Now you have to use distributed parameters to analyze this line. We have to use distributed parameter. Distributed circuit. I have to draw distributed circuit. Okay. The reason is its length is very large. Because of the large length, after every 10 kilometer or 20 kilometer, you will have different voltage and different current. Or maybe 100 kilometer, after 100 or 200 kilometer, let's say the line length is 2000 kilometer. So it's so long that you cannot do lumping. Now what you need to do is you need to understand it in partition. Problem is this. Okay, you need to understand it in partition. You cannot do lumping. You have to use distributed parameter. It means whatever the line resistance, inductance, capacitance or conductance, that should be distributed along the line. I mean, if you want to draw the model, then the model of this line has to be like this. RLCG. Not only this is the small part. This representation is for the small part of the line. Now again, okay, to analyze it completely, I have to use this model, guys. I mean, and so on. Okay, so you can see that what I have done is I have taken this branch for the small part of the line, and then again I have connected the same thing again. So I have distributed this. Okay, so the entire line is shown with the help of distributed parameter. Okay, so with the help of that I can analyze the long transmission line. Okay, you cannot do lumping. You cannot make the model like this. Okay, for the long transmission line. On long transmission line, the voltage and current is not only the function of time, it is also the function of position, because it's very large length. So voltage will also be the function of position. In short and medium, it was not function of position. We were not looking at the position because the line length was very small. If the line length is very small, then the effect of that position is neglected. Okay. But here in this case, the line length is very large. If the line length is very large, then voltage has to be a function of position as well. At what position you are looking. So voltage and current will be the function of time as well as space. Okay. So you have to remember this in long transmission line. Now the question is how to calculate voltage and current on the long transmission line. No, I don't want to go into that because there is a long derivation process. But I want to tell you the final result. What is the voltage and current on long transmission line? Let's say we have this long transmission line. This is my load side. This is my load side and this is my source side. Okay, this is our source side. This is sending end voltage Vs and this is sending end current Is. This is receiving end voltage Vr and the current IR, and this is ZL, load impedance. Now let's say at the source end you take x equal to 0. At this point you say x equal to capital L. It means you are looking from the source side to the load side. You are going from source side to the load side. Now if you are looking from this side and going towards this side, then if you want to check the voltage, let's say if you want to calculate the voltage, at some distance x, at this point, at some distance x, let's say you want to find the voltage, then you can remember the expression, guys. I don't want to go into the derivation of this. So voltage at some distance x is some constant V plus e to the power minus gamma x plus V minus e to the power gamma x. Gamma is known as propagation constant. Gamma is known as propagation constant and its value is root of R plus j omega L into G plus j omega C. Now this RLGC, they are the line parameter. You know that. Line resistance per unit length, that is R. Line inductance per unit length is L. Line conductance per unit length is Z, and line capacitance per unit length is C. शाहिल सर, लॉन्ग ट्रांसमिशन लाइन जो आपने बनाया उसमें RL सीरीज में कैपेसिटेंस पैरेलल में नहीं होगा, कैपेसिटेंस कंडक्टेंस पैरेलल में नहीं होगा, पैरेलल में ही तो लगाया, कैपेसिटेंस एंड कंडक्टेंस पैरेलल में लगाया, मतलब शंट में लगाया, मतलब ऐसा नहीं है कि भाई ये आपस में पैरेलल में होंगे, नहीं नहीं नहीं, उससे मॉडल बनेगा नहीं, ठीक है, उससे दिक्कत खड़ी हो जाएगी। एक लेक्चर लिया है मैंने, क्यों नहीं होगा ये एक नई, ये एक लंबी स्टोरी है, क्यों आप इनको पैरेलल में नहीं कर सकते, एक साथ क्यों नहीं लगा सकते, उससे दिक्कत हो जाएगी, ठीक है। तो उसके लिए मैंने एक लेक्चर भी ले रखा है, आप इस साल पूछा भी गया था ये PYQ, मतलब अगर पिछले साल का आप देखें तो उस साल में पूछा भी गया था ये क्वेश्चन, उसका मॉडल बनाया, तो मैंने एक सेशन लिया था, उसमें मैंने डिस्कस किया था इस चीज को। Okay, so guys, I told you that this is my propagation constant, and this is the expression for voltage as a function of x. Now this propagation constant has two parts, real part and imaginary part, J beta. Let's call it J beta. This alpha is known as attenuation constant, this gamma is propagation constant. Okay, propagation constant. Alpha is known as attenuation constant, and beta is known as phase constant. Beta is known as phase constant. Okay, so this way we have defined the propagation constant. Okay, now this is the expression for the voltage at some distance x, but I told you that voltage is not only the function of space, it will also be the function of time as well. It means if you want to write the voltage entirely, time as well as space, so what you can do is you can write it like this: V plus e to the power minus gamma x into e to the power j omega t plus V minus e to the power gamma x into e to the power j omega t. So what I have done is I have multiplied with j omega t. I have multiplied with j omega t to show that this as time harmonic wave. Okay, to make it time harmonic wave, I mean to introduce the time factor, you just multiply with this factor, multiply with e to the power j omega t. Okay, now if you take the real part of this, because this gamma can be broken into two parts, V plus e to the power minus alpha x into e to the power minus j beta x into e to the power j omega t. This is the first part. What about this? V minus e to the power alpha x into e to the power j beta x into e to the power j omega t. Now if you look at the real part of this part, okay, if you take the real, then this is the coefficient, you can say, so it will become e to the power minus alpha x into V plus, okay, V plus e to the power minus alpha x, and if you take the real part of this, it will become cos of omega t minus beta x, and the next is V minus e to the power alpha x into cos of omega t plus beta x. Okay, this is my voltage as a function of time and space. On the transmission line, on the long transmission line, this is the expression for the voltage. Now I have not derived it, but this is the expression for the voltage. Now this represents a traveling wave, we call it forward traveling wave. This is our forward wave, forward traveling wave. This is forward traveling wave, and this is backward traveling wave. Backward traveling wave. Okay, now let me show this, how it is changing with time and space. So we have the transmission line. Let's say I have the transmission line, and the transmission line is like this. Okay, and this is the transmission line we have, and here we have the load. And let's say there is a switch here, and this is our source side, okay, Vs. Now let's say we are closing the switch. As soon as you close the switch, then the voltage signal will travel on this line. We call it forward traveling wave. This wave will exist. As soon as you close the switch, forward traveling wave will exist on the transmission line. It will reach to the load. At the load, some wave will be reflected back. That wave is known as the backward wave. Under steady state, on the transmission line, you will have forward as well as backward. You will have the summation of these two waves on the transmission line. So if you want to look at the transmission line under steady state, then both the waves will be present on the transmission line, forward as well as backward. But backward wave will not be there if you are looking just after closing the switch. Just after closing the switch, only forward wave will be there. Backward will only be there if the wave has reached to the load and the load will give the reflection. Okay, I hope it is clear how the backward wave will come. Now let me draw this wave also, how it is traveling. Let me show you that. Okay, why I am calling this as traveling wave. So for that, what you can do is, for that let me draw it. So there is an exponential term, there is some constant v plus into this exponential term. So this will represent the envelope. Okay, so this is the kind of envelope on positive side as well as on negative side. Okay, so this is our envelope, and let's say this is x equal to L. At this point the load is connected. This is x equal to 0 and this is x equal to L. Okay, so I have drawn this envelope. Now inside this we have cos of omega t. Now if you look at a discrete point of time, let's say at t equal to 0 you are looking. At t equal to 0 it will become cos of beta x. Cos of beta x will look like this. Cosine wave, you know how to represent a cosine wave? Tell me guys. You all know how to represent a cosine wave? But that cosine wave is multiplied with this function. So the wave will look like this. At t equal to 0. At t equal to 0. Now let's change the time. If the time is at t1, then it will become beta x minus omega t1. Cos of beta x minus omega t1, because minus you can take common from the cosine, na? It will not change. So it will become cos of beta x minus omega t1. It means the delay, this wave is delayed by some omega t1 phase. Okay, at t equal to t1, it will become cos of beta x minus omega t1. It means it will be delayed by some omega t1 angle. Okay, tell me guys. Okay, it will be delayed by some omega t1 angle. Now at t equal to t1, if you want to draw the wave will look like this. You can see that the maxima has traveled by some amount at t equal to t1. Now at t equal to t2, this will become omega t2 minus beta x. So you can take minus common, so it will become cos of beta x minus omega t2. Omega t2 is again some angle phi 2. It means again it will be delayed by some angle. So if you draw the wave at t equal to t2, then the wave will look like, let me draw it with this color. The wave will look like this at t equal to t2. At t equal to t2, this is the wave we have. Okay guys, so you can see that if you are not moving the time in discrete position, let's say the time is moving continuously, if your time is changing continuously, then you will see that this maxima is traveling towards the load side. The maxima is traveling towards the load side. That's why we call it forward traveling wave. Okay, forward traveling wave. And the interesting part is, as it travels on the transmission line, its amplitude is decreasing. Its amplitude is decreasing because of this alpha. This alpha is known as attenuation constant, because it will attenuate the amplitude of the signal. After reaching this point, after reaching this load point, some wave will be reflected, some amplitude will be reflected. Okay, And that reflected wave will look like this. Let me show that reflected wave also. That reflected wave will look like this. Okay, this is the load point. Again, you have to draw the exponential. I mean, the wave is now coming on this side. Okay, and the replica. This is the load end. Okay, now you have to draw the replica. Okay, guys. Now, after reaching the load, some part is reflected. So the reflected wave I'm showing like this. Let me show the reflected wave as well. So the reflected wave will be like this. It will be reflected back. It's traveling on backward direction. It is traveling on this side. At t equal to 0, let's say, at t equal to some instant, maybe some t3, t4, t5, whatever. Okay, at that instant, this is the wave. Now, after some time, there will be some other backward wave, and that will be, I mean, this wave will shift. The maxima is shifting on this direction. Okay, so you can see that this wave is traveling on backward direction. But you are looking that, sir, with x, the amplitude is increasing. If you are looking on this from this side, because x is positive in this side, no? If you are looking from this side, it seems that it is increasing. It seems that it is increasing, but actually it is traveling on backward direction. If it is traveling on this side direction, its amplitude is decreasing in this direction. Okay, so it has decreased in this direction, then it will go back and it will further decrease the amplitude. I hope it is clear. But if you are looking from this side, it seems that its amplitude is increasing. Okay, but actually the wave will go from this side to this side. So we have to look from that side to this side, and its amplitude will decrease. I hope it is clear, everyone. So I told you there are two waves, backward and forward wave. Okay, this is the backward traveling wave and this is the forward traveling wave. Now if you want to calculate the speed of the wave, at what speed the wave is traveling, so for that what you can do is you can make it constant. Make this phase constant. This is the way you can check the speed. Okay, omega t minus beta x is equal to some constant, and if you take the derivative, dx by dt will be equal to 0. From there you can calculate the speed of the wave, that is omega by beta. Okay, this is the speed of the traveling wave. At this speed the wave will travel. Why you call this alpha as attenuation constant? I told you, because it is responsible for decreasing the magnitude. If alpha is 0, let's say, then there will be no decrement of the amplitude. That's why we call it attenuation constant. What is this beta? Beta is known as phase constant. Beta is known as phase constant. So what do you mean by phase constant? Phase constant is simply, you can say, phase constant is change in phase per unit length. This is change in phase per unit length. Per unit length. This is known as beta. Beta is change in phase per unit length. Now how to calculate this beta? We know that in any wave, if you are moving lambda length, then the change in phase is always 2 pi radian. Because if there is any wave and if you are moving one wavelength, then the change in phase is always 2 pi. If you are moving one unit length, then the change in phase will be 2 pi by lambda. So this 2 pi by lambda is called beta, phase constant. I hope it is clear, everyone. So the phase constant beta is 2 pi by lambda, and this is how we are going to calculate it. Okay, so this was again interesting. So you have to remember the beta, what is beta, okay, and what is alpha. I told you the meaning of alpha also, attenuation constant, and how it is related to the traveling wave. Okay, now let's go ahead a little. I told you about voltage. What is the voltage expression as a function of x on long transmission line, space and time? Okay, what is the current expression? Current expression is also similar to that. Okay, let me tell you guys, what is the current expression? The current expression will be, we know that the voltage expression with x is equal to v plus e to the power minus gamma x plus v minus e to the power gamma x. This was the voltage expression. What is the current expression? The current expression is again similar to that, I plus e to the power minus gamma x plus I minus e to the power gamma x. Okay. This is my voltage expression and this is the current expression. Now, with the help of voltage and current expression, what I can say is, there is a relation of voltage and current. And what is that relation? There is a relation between voltage and current. What is that relation? The relation on the transmission line is, if you take the change of voltage with x, that will be equal to minus of R plus j omega L into Ix. This is the relation of voltage and current on transmission line. And similarly, you can also write it like this. If you take the change of current with x, this will be equal to G plus j omega C into Vx. Okay. This is the voltage expression on the transmission line and it is related with the current like this. Similarly, this is the current relation and it is related with the voltage like this. Now what I can do is, from here, if I take the derivative of this, dix by dx, so obviously I have not derived these relations because it will take more time, so I have written them directly. Okay, so I have to remember them directly. On transmission line, these relations are valid. Now, if I take the derivative of this expression, current expression, that derivative will be equal to gamma I minus gamma I plus e to the power minus gamma x plus gamma I minus e to the power gamma x. Okay. If I take the derivative, it will look like this. And I can write it like this. This must be equal to minus of G plus j omega C into Vx. And Vx is this, V plus e to the power minus gamma x plus V minus e to the power gamma x. Okay, we can write like this. So you can see that I have calculated di by dx. From this Ix expression, I have calculated di by dx. That must be equal to minus G plus j omega C into Vx. Now if you look at this equation, actually it's a single equation, but in this single equation there are two equations embedded. This e to the power minus gamma x term and this e to the power minus gamma x term. The coefficient of e to the power minus gamma x on this side and this side will be same. Similarly, the e to the power plus gamma x and plus gamma x on this side, they will be same. So it means in this one equation, there are two equations embedded. So what you can do is you can separate these two equations. So if I separate these two equations, I will get minus gamma I plus, this is the coefficient of e to the power minus gamma x, must be equal to minus V plus G plus j omega C. Okay, and if you take the coefficient of e to the power gamma x, then you can say that gamma into I minus must be equal to minus of G plus j omega C into V minus. Okay. Now from here, this minus is gone, and if you calculate V plus upon I plus, okay, that will be equal to gamma divided by, gamma is root of R plus j omega L G plus j omega C divided by G plus j omega C. Now what is this value, guys? This value become root of R plus j omega L divided by G plus j omega C. Okay, this is the value we got. And this is V plus over I plus, or you can say that it is also equal to V plus e to the power minus gamma x divided by I plus e to the power minus gamma x. So what is this? This is the ratio of forward traveling wave to the forward traveling wave voltage divided by forward traveling wave current. It means it is the impedance seen by the forward traveling wave, and this is this value. It is the impedance seen by the forward traveling wave. Similarly, from here you can calculate V minus over I minus. That will be equal to minus O, because there is this minus will not cancel. In this minus will cancel, but here the minus will be there. It will be R plus j omega L divided by G plus J omega C. Okay, this is V minus over I minus, and this is V plus over I plus. Now this is the impedance seen by the forward traveling wave. This is the impedance seen by the backward traveling wave. Why I am calling it impedance? Because you can see that R plus J omega is in ohm, this is in mho. So it is ohm divided by 1 by ohm. So it will become ohm square, and take the root, you will get the unit as ohm. So this is an impedance. Okay. So the impedance seen by forward traveling wave is this, and the impedance seen by backward traveling wave is this. Now what is this quantity called? This quantity is called as characteristic impedance of the line. Okay, this is known as characteristic impedance of the line, or surge impedance, sometime you can call it. Okay, characteristic impedance. Characteristic impedance of transmission line. What is the characteristic impedance of the transmission line? That is root of R plus J omega L divided by G plus J omega C. This is the characteristic impedance of the line. Okay guys, and if you want to define the characteristic impedance, let's say, so one definition is this formula. The other definition is, it is the impedance seen by forward traveling wave. Whatever the forward traveling wave, the impedance seen by that wave is characteristic impedance, and the impedance seen by backward traveling wave is negative of the characteristic impedance. Okay. Now you may ask, sir, where this is located, where this characteristic impedance is located. This characteristic impedance is located nowhere. It is the characteristic. Characteristics, things are not located anywhere. Okay, they are the characteristics of the line. So it is located nowhere. Okay, but it governs the energy flow, power flow. Okay, it governs the energy flow and power flow. So I told you what is the meaning of characteristic impedance and how you are going to calculate the characteristic impedance of the transmission line. That is R plus J omega divided by G plus J omega C. Now let's come to the next thing. Next thing is lossless transmission line. Let's take the case of lossless transmission line. Okay, lossless transmission line. Let's take the case of lossless transmission line. So if you look at the transmission line, which component are the lossy component? This R is the lossy component, Z is the lossy component. So what you can do is, you can take R equal to 0 and Z equal to 0. Then it will become lossless transmission line. It is called lossless transmission line. If you take R equal to 0, Z equal to 0, then gamma, what is the propagation constant? It will be R plus, this was the formula, G plus J omega C. Now you can see that R is 0, G is 0. So it will be purely imaginary, G omega root LC. Okay. So it is equal to J beta only. It means alpha is 0. So there is no attenuation on lossless transmission line. On lossless transmission line, the wave will not attenuate. This attenuation will not be there on the lossless transmission line. If R is 0 and G is 0, if the line contains only L and C component, then there will be no attenuation. Alpha is 0, only beta will be there, and beta, the phase constant, beta will be equal to omega root LC. Now one interesting thing will happen. We know that the speed of the wave is omega by beta, the speed by which it is traveling on the transmission line. So now what is the speed of the traveling wave, guys? Beta by omega. You can calculate, omega by beta. Omega by beta was the expression for the speed. So speed of the wave is omega by beta, and if you calculate, it will be 1 by root LC. It is very interesting relation. It means on lossless transmission line, L and C will decide the speed of the wave. L and C of the line will decide the speed of the wave. And how to calculate L and C? You know how to apply GMD, GMR, and how to calculate inductance and capacitance of the transmission line. So that L and C are responsible for the speed on the transmission line, for the speed of the wave on the transmission line. I hope it is clear. Okay. So I told you what is the meaning of lossless transmission line. Now on lossless transmission line, what is the characteristic impedance? This is also known as surge impedance. Surge impedance. So for lossless line, we know that the surge impedance ZC or Z0, whatever you call it, This R is 0, G is 0, J omega L divided by J omega C, J omega will cancel, it will become L by C. And it is purely a real quantity. It is purely real. Is it clear, everyone? It will become root of L by C. And it is purely real. Okay? So we found the surge impedance on the lossless transmission line, and we found gamma, or you can say alpha is 0 and what is the beta. Okay, we have calculated this on lossless transmission line. Now it's time for ABCD parameter of transmission line. ABCD parameter. Now how to calculate ABCD parameter? How to calculate ABCD parameter? In ABCD parameter, we have sending end side and we have receiving end side. We know that this is the transmission line. Okay, let's say this is our transmission line. This is the load side. So we have this receiving end voltage and this is the receiving end current. And on this side we have the source. So we have this source voltage Vs and this is the source current Is. Okay, is it clear, everyone? Okay, so we have found now for ABCD parameter, what you need to do is I need to write Vs and Is in terms of VR and IR. Okay, so I need to calculate these ABCD parameter of the long transmission line. Now how to calculate them? It's very easy. We know that Vx is equal to, if you look at the voltage as a function of x, then Vx is equal to V plus e to the power alpha x minus alpha x into e to the power minus j beta x. I told you that this is the expression for Vx. No? So what I have done is I have put gamma equal to alpha plus j beta, and I have separated alpha and beta part. Or for the time being, let's not separate them. Let's write directly like this: minus gamma x plus V minus e to the power gamma x. And what is Ix? Ix is I plus e to the power minus gamma x plus I minus e to the power gamma x. We know that. This is the expression for current, this is the expression for voltage. Now we have understood that V plus or I plus is Zc. So what I can do is, I can replace this I plus as V plus by Zc, e to the power minus gamma x, and this I minus, it can be represented with minus of V minus by Zc, because we know that V minus or I minus is minus Zc. So minus Zc is taken in the denominator and that will give you I minus. Is it clear, everyone? This is Ix. Now what you can do is take this Zc on this side. So if you take this Zc on this side, it will become Zc into Ix, and that will be equal to V plus e to the power minus gamma x minus V minus e to the power gamma x. Okay, this is the relation. And one more relation is this: Vx equal to V plus e to the power gamma x plus V minus e to the power gamma x. Now what I want to do is, I want to put x equal to 0 on both sides. At x equal to 0, if you put x equal to 0 on both sides, this current will become I0. I0 means I sending. X equal to 0 means sending end current, sending end. So if you put x equal to 0 in this, it will become Is. So Zc into Is is equal to V plus minus of V minus. And similarly, if you put x equal to 0, it will become sending end voltage, Vs. That will become V plus of V minus. Okay. Now from these two relations, you can calculate the V plus and V minus value. You can calculate the V plus and V minus value. So what is V plus value, guys? If you calculate V plus value, that will be equal to Vs plus Zc into Is by 2. And V minus value is Vs minus Zc into Is by 2. I hope it is clear. These two relations are important now. We are going to use them. So we found V plus and V minus. Now we can put these values here and calculate the Vx expression. So if I put these values here, then Vx will be equal to V plus. What is V plus? V plus is Vs plus Zc into Is by 2 into e to the power minus alpha x into e to the power minus j beta x. Or you can write e to the power gamma x. Okay, e to the power minus gamma x plus V minus. V minus is Vs minus Is into Zc divided by 2 into e to the power plus gamma x. Now what we can do is, we can take this Vs common. So if you take this Vs common, then you have Vs into e to the power minus gamma x plus Vs into e to the power plus gamma x divided by 2. Okay, you have this quantity. And if you take this common, Zc into Is, if you take this common, then you will have e to the power minus gamma x by 2 minus e to the power gamma x by 2. Okay. Now it will become cos hyperbolic gamma x. So Vs cos hyperbolic gamma s, and it will become minus sin hyperbolic gamma s minus Zc Is sin hyperbolic gamma x. Okay. This is my Vx. Now if you put x equal to 0 on both sides, if you put x equal to capital L, let's say, if you put x equal to capital L, so if you put x equal to capital L, then you are at the receiving end. So at x equal to capital L, this will become VR. VR will be equal to Vs cos hyperbolic gamma L minus Zc into Is sin hyperbolic gamma L. Okay. So we have calculated VR in terms of Vs and Is. Similarly, you can calculate the current IR. You can calculate the value of current IR, and that will be equal to, let me write again, I mean in this expression, I plus and I minus, in the expression of current, you can put these I plus and I minus like this. Okay, this is my, yes, this is my Ix. Now here you can put the value of V plus and V minus, and you can separate it out. So you will get IR is equal to Vs by Zc, and this is also minus sin hyperbolic gamma L, you can check it yourself, plus Is into Zc, no, this Zc will not be there, plus Is into cos hyperbolic gamma. Okay, so you'll get this. Now if you write this in matrix form, so this is my VR, this is my IR. We have calculated VR and IR. Now if you write this in matrix form, then you will get VR IR is equal to cos hyperbolic gamma L minus Zc sin hyperbolic gamma L minus 1 by Zc sin hyperbolic gamma L and cos hyperbolic gamma L into Vs Is. Okay, we can write it in matrix. So if you want ABCD parameter, then you need to calculate Vs Is in terms of VR IR. So what you need to do is, you have to take the inverse of this and multiply on this side. So if I take the inverse of this, what I will get, you can calculate Vs Is from here, and if you calculate the inverse, let me write the inverse directly. It will become cos hyperbolic gamma L. This is also cos hyperbolic gamma L. This will become Zc sin hyperbolic gamma L. It will become 1 by Zc sin hyperbolic gamma L. This is the inverse, VR and IR. Okay, I hope it is clear, guys. So we have calculated the inverse of this and multiply on both sides. So Vs Is will be this. So this is our A, this is our B. So you can see that this is our D. So you can see that A equal to D. And if you take the determinant of this, AD minus BC, that will always be 1. You can check it. And we found the ABCD parameter of the long transmission line. Now it is very helpful. So in long transmission line, A equal to D and AD minus BC is equal to 1. So you can see that you can say that the long transmission line is symmetric. Long transmission line will be symmetric and it will also be reciprocal. It will also be reciprocal. Okay. So the long transmission line will always be reciprocal and symmetric. I hope it is clear. So I told you how to calculate ABCD parameter of long transmission line. Okay. So guys, I think it's time to stop here. We have discussed long transmission line I have told you in short span, in 45 minutes, I just told you how the long transmission line formulas are derived and how you are getting these formulas. So something I have missed, because everything is not possible in 45 minutes. Okay. So that's why I have not derived these expression, from where this expression came. Okay. From where this expression came, I have not derived it. From where this expression came, I have not derived it. Okay. But I have given you some important formulas, like I have told you traveling wave, forward and backward, why it is traveling. And next I told you about the propagation constant, what is the meaning of propagation constant and what is surge impedance. Okay. And for the lossless transmission line and the speed on the lossless transmission line, okay, that I have told you. And then ABCD parameter, how to calculate ABCD parameter, I told you on the transmission line. Okay. So at this point, let's stop the class. I hope you enjoyed. Don't forget to subscribe our channel and like this session. We have our mobile app also. So go to the Google Play Store, download the mobile app and search this BYJU'S exam prep. So you'll find the mobile app. You can download that app and then you can watch the free lectures on mobile app also. Okay. So that's all for today's session, guys. See you in the next session. Next session will be on Monday. So thank you and take care. Bye.